Hello everyone. This video I'm going to show you demonstrate some homework problem. Here is I think is 9 point. Oh, what's the number? Yeah, 9.36. Okay. This is not this one. 9.36. Okay. 9.36 is there a spacecraft. Okay, this spacecraft consists of two parts. One is orbiter and the other is lander. Okay, and give you the mass of the orbiter and the lander. And you say some explosive, maybe some explosive happens, maybe slow explosive happen between the spacecraft. Then separate into two parts. Okay, the orbiter and lander then separate. And after the explosive, the orbiter's velocity is this one. It gives you the velocity vector and the lander's velocity vector in this one. It says find the velocity of the composite spacecraft before the separation. Okay, this is a very typical. This is a very typical, let's say, momentum conservation problem. I think I can do the calculation on this screen. Let me see. Okay, so let's do the calculation on this screen. Okay, and we can just simplify this problem. Sorry, not simplify the problem. We can express the problem like this. Okay, so initially you have spacecraft. Okay, you have two parts. That's called m plus m. And then after some explosive happens, it will become separate. Okay, and the V and the V. Okay, V. Okay, so it's and explosive. Okay, explosive is an internal force. Okay, explosive is an internal force. Okay, no external. So this system there is no external force. Explosive just internal force because it explodes from inside, so it's internal forces. So this system is there is no external force acting on this system. So if you use a system, so the system is isolated. So once the system is isolated, it's tell you the momentum conservation. Okay, so initial momentum is equal to the final state momentum. Okay, and momentum is a vector because right now this problem looks like it's a 2D problem. It gives you the velocity vectors and it's only two dimension. Okay, I think I just want to simplify the problem. So it's only two-dimensional problem. Okay, and let's say though we treat the orbiter because it has a bigger mass, so we give capital M. The lander is a small mass, we give it a small m. Okay, so he want to give you after the explosive, he give you the velocity vector of the lander and orbiter and calculate what's the basically you just want to calculate this Vm plus m equal to what? Okay, he give you the velocity vector after explosive and give you the mass. Okay, he want to let you to calculate what's the velocity vector of the spacecraft before explosive. Okay, and before explosive and after explosive, the momentum is conserved because there is no external force. Okay, so we can write down the equation. So before explosive, the system is m plus n. Okay, and times its velocity vector, m plus m, and equal to the velocity equal to the momentum after explosive. Okay, I think that's the equation. I think the difficult part is because it's a vector representation, but we have to make it become a component representation. Okay, we have to do the component by component. Okay, so I think that's a problem. Vector calculation always confuse everybody. So, okay, so let's me write down. Okay, use the component expression. Okay, so this is x m plus m and I plus, sorry, it's velocity, not position. Okay, okay, equal to V m plus m, but it's x component I plus V m plus m, but it's y component and j. Okay, same thing, we can write the component expression for the vectors for the capital M and M, that means orbiter and lambda. So there is M x component I plus Vm y, and this is j, and this is m small m x I plus small m y and j. Okay, so we use the component expression for the velocity vector of the spacecraft, orbiter, and lander, and then we can use. Okay, so from the x component, okay, we do from, okay, maybe change the color. We start with the x component. Okay, x component. Okay, x component. Okay, so x component, we do the momentum conservation. X component is m plus n times v m plus n x component equal to capital M times the v. Okay, be careful. We now only do the component x, because that's the feature of the vector calculation. You will do component by component. So x component equal to x component. So x component is v capital M x and plus small m, and be careful, it's v small m and x. Okay, that's the x component, and then we do the y component. Y component is m plus n times v m plus m, but it's y component, and m plus capital M y component plus small m and m y component. Okay, okay. So do we have enough information to solve the problem? I think we have, because okay, n plus n, we have capital M is 784 plus 392. The v plus m, the spacecraft x component, we don't know. Okay, that's that's unknown. And this one is 784 times vmx. So after the explosive, what's the x component of the orbiter? The x component, so it's 225. Be careful, it's 225. And the lander 392. Okay, what's the velocity, x component velocity, x component of a velocity of the lander after explosive? It's, be careful, it's minus 75.4. Okay, so in this equation, we only have the one unknown, one equation, so we can solve the v plus m x very easily. So the same thing, we do the y component 392, and it's am plus m y equal to 784. So what's the y component of the orbiter after the explosive? So it's 107, and in orbiter 392. And what is the velocity y component of, what's the velocity y component of the velocity of lander after explosive? I think it's minus 214. Okay, so we can solve the v m plus m max and the v m plus m y out. So I think this answer m plus m x is, I think you can add the calculator. Let me see the calculator. 784 times 225 and minus 392 times 75.4. Okay, and divided by total mass. A4. Sorry. 392. 124.86, right? Okay. Okay, so it's 124.86 and is meter per second. Okay, and what's the Vm plus my? M plus M y. Let's do the calculator. Say 4 times 107 minus 214 times 392. Yeah, that's exactly 0. Okay. So the x component of the spacecraft is 124.87 meter per second, and the y component of the spacecraft is the 0 before explosive. So yeah, there's no component. So the magnitude. Okay, if you want to calculate magnitude of the velocity, okay, let me. Okay, so if you want to calculate magnitude of velocity, just don't forget how to calculate magnitude of velocity. Just v m plus m. If we want to calculate its magnitude, it's equal to the 124.87 square plus 0 square. Okay, but in this problem, it's just equal to 124.87. Okay, x component square plus y component square, and then take a square root. That's the magnitude of velocity. If you have the x component of velocity and y component of velocity, and that's the way you calculate the magnitude of velocity. Just don't forget how to calculate magnitude of vectors. But in this problem, y component is 0. Okay, that's very easy. But it's not. It's hard to say every time you have a 0 component. You have a zero component. Sometimes, yeah, it's just very simple case. Okay, so find the velocity. So we find the velocity of the spacecraft before separation. Okay, and we also calculate its component of a velocity, right? Okay, so this is a very typical problem for momentum conservation. Okay, so and this you have to be careful. You have to do the momentum conservation in x direction and y direction. Just list the equation for x direction and list another equation for the y direction, and then be careful what is your x component what x component for the orbiter and x component for the lander. Just be careful, don't put it in wrong numbers. Okay, yeah, I think sometimes I still found some students just put the wrong number. It's an easy problem, but it's put the wrong number in there, and still doesn't got the answer. Okay, so this is the video. Okay, see you in another video. Bye bye. Oh. Mm-hmm.